Welcome to the 2024 Community Summit, and thank you for joining us for our featured ECL workshop, Sleep Well with ECL, Job Automation and Scheduling. My name is Bob Foreman, and I am a software engineering lead and ECL trainer at LexisNexis Risk Solutions for the past 13 years. I'm so happy you are here because we have a great session lined up for today. This workshop spans the theoretical to the practical, best ideas to best practices, and a very STEM to stern look at what can be done with ECL and HPCC. We assume you have a little experience with ECL, but even if you don't, please don't worry, as I will be giving a very thorough examination of today's code in our next 2 hours. For most of the presentation, I'll be turning off my camera so you can focus on the content, and I'm going to be moving around to our ECL environment back and forth to demonstrate code as we navigate between the slides and our presentation of code. So without further delay, let's get started. Let's have a look at today's agenda. This workshop teaches the work unit scheduling and process automation aspects of the ECL programming language. There are many tools to allow you to standardize, optimize when and how a given set of tasks can be most efficiently accomplished within your production environment. We're going to start by introducing the job scheduling syntax in ECL, which teaches you how to launch a work unit at a specific time or repetitively based on time periods, such as every hour, every 5 minutes, and so on. And we're also going to introduce event-driven ECL syntax that lets you launch work units when a specific event occurs. It then applies these techniques to an extended real-world set of tools that automatically sprays files that appear on your landing zone and processes them to automatically add them to your existing production data. So this project was a labor of love that was started many years ago by the author, Richard Taylor. Now, in case you don't know, Richard Taylor has been working with ECL for, over 24 years, and just recently, July of this year, he retired, went into retirement. This was his last piece of work that he submitted to the ECL community. I took on his writings and his code examples to wrap everything I could into this 2-hour workshop. This workshop, the presentation, the repository that I'm going to show you, has everything you need to take his best practice skills and use them in a real-world production environment. Like I said, this thing started way back in 2015, and Richard spent a lot of months upgrading this to our current 2024 best practices and standards. Thank you, Richard, and I guess he's somewhere traveling the world right now, and we wish him very well, and just wanted to give him a warm acknowledgement before we get started. Now, you can follow along with this workshop presentation, and I encourage it, if you have an environment already set up. It was kind of problematic to set up a cluster that anyone around the world could get to because of, frankly, security reasons. We're going to be doing some things behind the scenes and under the covers with our landing zone and with the events that go back and forth between the HPCC components, so we have some security built in. So I would encourage you to, first of all, visit the GitHub repository that contains all of the code that you need, and there's the link on this slide. Now, I'm also going to put this link into the chat during the rebroadcast of this and in the recording, actually, that you're watching right now. So you'll see a link to this, and you can go right into this GitHub repository, download the repository. Now, in case, we'll take you over there real quickly. Here's the GitHub repository, and once again, you can either clone it if you wish, or you could just download the zip file and extract the zip file on your local machine, and then preferred environments, either the ECL IDE or VS Code. You can then access the code folder, well, which is part of the root folder. You'll actually open up the root folder, which will then give you access to the code folder and then all of the ECL contained therein. All right, so here's an example on the right side here as to how you would add the folder in the ECL IDE. If you're using VS Code, you'll simply open the folder into your environment. Well, automating standard processes to run without anyone's oversight is all about knowing when to launch the process. And in ECL, we have a number of workflow services, but there is a special workflow service that does this very thing that we need to do. It's called the When Workflow Service. It looks for a particular event or the existence of a data set and then executes the particular action. So in addition to the When Workflow service that we're going to be demonstrating, first of all, you append it to any ECL action. It must be an action, not a definition, that could delay its execution until the appropriate time, either by a cron event, which is time-based, or a user-defined event using, well, we're going to talk about two functions here. One is called notify, and the other one is called event. This workshop will show you how to automate the processes and schedule the job. We're going to be dividing this workshop in 3 stages. First, we'll take a quick look at cron jobs. And actually, I'll launch one. We'll have one running in the background while I continue with the workshop. And we'll check back on that cron job periodically to see how it's doing. Also, instead of time-based events, I'm also going to show you how to launch jobs when you have a user-defined event. And that user-defined event is more significant because then in real-world examples, we're going to actually demonstrate to you production-ready code. This was code that we wrote for one of our groups in LexisNexis to automatically detect the existence of a file on the landing zone, automatically spray it to the cluster, and then automatically process it using all kinds of different things. We're going to be looking at superfiles. We're going to be looking at the fundamentals of not only just event-driven stuff, but we're also going to be looking at using projects and using different types of transformation and also the mechanics of working with superfiles. So there's much, much more besides just the event handling. We're going to be looking at all aspects and a wide range of best practice ECL design. All right, so if all of you are ready, get into your most comfortable chair, grab your favorite beverage. Let's get started with the first topic, the topic of cron jobs. All right. Cron jobs, of course, surround itself around the cron function. The cron function takes a single string parameter, space delimited, and those 5 parameters are the minute, number 1, the hour, the day of the month, the actual month, and finally the day of week. All right, so more detailed as to what range of numbers. They're all integers here, and you'll see a lot of cron calculations because we want sometimes these events to be repetitive every 3 hours, every 5 minutes, and so on. So you'll see a mathematical expression that will just simply cycle through, and if the number hits an integer, then it will fire the cron event. So omitted settings, we just put an asterisk. Things that we're not concerned with, for example, the month or day of the week, we just put an asterisk there. Now, our first bit of code that we're going to take a quick peek at is the every module. The every module we actually copied from the documentation of the language reference manual. We saw the example usage and we decided to take it and just kind of tweak it a little bit to fit our demonstration. So we have a module that passes a unsigned 1 numeric into the module, and whether we drill down to one of 3 definitions, day at, hours, or minutes. So the usage of this, by passing to the every module a numeric, the first example here, day at, every day at 2 a.m. So the numbers are from 0 to, of course, 24 or 23. And then every 3 hours, we just put the every 3 hours we want something to happen. 15 for the third example, every 15 minutes, every 15 minutes. Now, in order to verify and validate the code that we're working with, here's the first of many utility functions that Richard put together to document the event handling that he was trying to demonstrate. So as you see here, we have a function called logout. And it's simple but very, very powerful. We start with a record structure that has 3 fields. We have a comment field, and then referencing from our standard library functions, the today function, which then puts the date into an unsigned 4, and the current time, which puts it into the standard time format, which is an unsigned 3. We define a data set called DS with the dataset statement, and then as we get our string that gets passed into the function, we trim it first, append a space to it, and then append and add or concatenate the current date followed by a hyphen and the current time. We then will write this to our ECL agent, which we're using a built-in function called system.log.dbglog. All right, and we pass it the log string. And so we wait for the existence of the data set, which once this logout function is called, it will always have default values in it. When that data set is detected, it will automatically execute the action called AGT_log, which is calling the ECL agent, which is calling the log string, which is built from the parameter that's passed into the function. All right, pretty nice, and it works wonderfully, as you're all going to see. So let's demonstrate cron. Cron is pretty simple. I'm going to go ahead. We have a very, very, very easy BWR file here. We import the standard library reference so we could, actually in this case, I don't think we really needed it except for drilling down to logout, but logout was importing as well. We may not even need that import there, but anyway. The output here of the login, we've just got a 2-minute run message that we're going to put in. We're going to document the date and the time that the event was logged. And so then the magic behind this is the when workflow service. You can see on the far right side of each one of these output statements a when workflow service that's calling cron. Cron calling into the every module. The first example will give us events every 2 minutes. Next, we'll have an event every hour. Now, in this 2-hour workshop, if I leave this running, we should see an event posted after 1 hour. Of course, the third event, if you happen to be running this around 12 noon, you'll see an event posted there as well. UTC time, by the way. That's always documented in the language reference manual. However, we're definitely going to see the 2-minute run. We're definitely going to see the hourly run as we execute this. Now here it is in my ECL IDE. I'm using the ECL IDE. It's been our flagship IDE for many, many, many years, although I know a lot of people are now starting to migrate to VS Code with the ECL extension because of the many things. First of all, multi-language support, and secondly, the automatically inclusion of the generative AI support. But the ECL IDE I like to use as a good teaching tool because it is very sparse. I can make the IDE sparse and we can focus on ECL. So you see right here, I've already loaded my BWR cron job from the last slide that we just looked at. And always good practice for even seasoned ECL developers is to first do a syntax check. We have no errors at the bottom, and I can now submit this to my training cluster. And something interesting happens here. You'll see at the bottom next to the Builder tab, a kind of a do not enter icon here, this red icon, which tells us actually in this case it's not really being blocked. It's kind of in a wait state. We really don't have an icon to designate that something's waiting, but we can definitely see this, that as I take a look at this a little bit later on, you'll see that in the ECL watch that we'll actually see this job loaded up into the ECL scheduler because of the when workflow service. And in about 2 minutes time, we'll see our first event. We can then scan that, look at it, and then continually to go back to that and see, maybe after an hour's time, we'll see the 1 hour event. So now, through the magic of movie making, let's take a look at the ECL watch. I've given it a few minutes to run, and we'll start with the ECL watch, the cluster I'm using, looking directly at the event scheduler. This is right on the front page of your ECL watch. It is the tab right next to activities, which is your main page. And you'll see that we have 3 jobs being run, 3 outputs, 3 cron events that are trying to be detected. So the first one up at the top we have is the, I believe it's going to be, that's the hour one, and then we have every 3 hours, and we have the minutes. We could take a look at the ECL work unit itself, and you'll see here is my cron job at the very top of this ECL list, and I go into the outputs, and you'll see that in the time I just finished talking and a little delay and resuming my recording, you'll see here that there have been several 2-minute run events that have already been posted. Even though going back to the ECL, we're still in kind of a wait state here. We're not really able to look at any events here per se until the work unit has stopped. So when you want to look at events during your time here, you'll go into, of course, your ECL watch. So we can verify that things are up and running, cron is working. Then you'll see that later on we'll be able to go into other outputs here, and hopefully in an hour's time we'll see the hour event being posted. So you can see cron events are pretty easy to work with. Let's take a look now at creating our own custom events and using notify and the event function to work with these user-defined events. So triggering a job at periodic intervals, of course, is very, very useful. But we need more control if we want to automate processes. So we also need to be able to launch jobs that do not have a regular period, and launching these jobs on demand. How do we do that? How do we control it? So we have a special function called notify. Actually, I believe notify is an action, and we trigger specific events from the ECL code using this notify action, sending an event to your cluster work unit wide. Any work units that are waiting for events will get notified that an event has been posted, and then if your work unit is looking for that event, it will automatically execute the particular action that it's waiting for. So there's a BWR example we're going to look at together. It's introducing the use of the notify action to trigger a specific event, and then the ordered action to both launch the actual work and then log it. So to do this, we're going to set up a cron job that fires once a minute, and we're going to detect if the minute is even or odd. And based on even or odd, we'll post an event that the event is even, the event is occurring odd, and so on. Very, very simple example. Here's BWR notify jobs, and there's a lot to unpack here. First of all, at the top, if you've never seen this before, the hashtag work unit template language statement allows us to name the work unit, making it easily identifiable on the ECL watch. There's several other useful purposes for hashtag work unit, so you should take a look at the documentation. The next block of code here is called setting up the job. And you'll see here that we have a set of events, launch even and launch odd. And based on the time that it's occurring will then pick one event launch even or one event launch odd. Very, very simple, binary choice. We have the current time, we also have the minute, and we'll be appending all of this information into a field called work text, or work text, WORKTXT. During this time, we'll also be outputting even or odd. You see there's just two output statements here. When the particular event is detected, when an even event is detected, it will launch the even and the work text, and then odd and the work text. The magic behind this is in triggering the events. The launch job definition defines the notify action that fires the event defined in the myEvent definition. Its second parameter is just an asterisk to indicate there's no further information with the event. And since this action has a definition name called launch job, it is not a direct action like the first two output actions that we were looking at. All right, and will only be executed when its definition name is called by the ordered action. So down at the bottom, we have the log text definition that just defines the text for the logout function used in the log event action. And note that the output action in the log event definition does use named and extend options, but does not have the when workflow service appended to the definition. This creates the extensible log of event triggers for the particular work unit. And finally, near the bottom here, we have the ordered action. This does have the when workflow service appended. So the two actions it lists will only execute when the specified cron time arrives, which we know now is once a minute. And when it triggers, the actions listed in the ordered action parameter execute in the order that they appear. And we use the ordered action instead of sequential to avoid any side effects that may occur. The launch job action fires the events defined as myEvent, and whatever action in the same or any other work unit, it's waiting for that myEvent value and will trigger and do the work. So when myEvent is launch even, the first output executes, and when myEvent is launch odd, the second output executes. And after the launch job action, the log event action then adds the fired event to the notify run list of events it is logging. And as you can see, this code is almost the same. This one called BWR_job launch as the previous example, with changes marked here in bold, where we're demonstrating the use of something called the event extra function. So we're just going to address the differences in this code from the previous one. The first difference to note is in the launch job definition that defines the notify action to trigger the event now has a second parameter that's replaced the previous asterisk with the event extra definition, event EX definition that creates the XML string containing the extra information to pass to the event. Event extra requires it will send the information defined inside an XML tag. And that's what we're doing there. You see it says extra, event extra, even odd, and a couple lines above you actually see the generated or the XML sample that we have there that identifies the even odd tag. The notify second parameter requires either an asterisk as a string constant or an XML string containing a single set of event tags. Between those event tags, you can format any data you want to pass to the specific launch instance by placing it within any tags you choose to use. But you can't use XML attributes since the XML stream will be parsed by the event extra function, which only takes the tag name as its single parameter. And the event X definition builds its XML stream from the info and extra definitions. Then when the event triggers, the work text definition uses the event extra function to get the information from the specific event instance that launched the job. And in this case, the contents of the even odd tag is in the XML string. The when workflow service on both output actions use the event function to wait for the myEvent text to happen. So even though these are direct actions, they will not trigger until the proper value of myEvent occurs. And these event functions still have asterisks as their second parameters. If you wanted to be more specific in exactly when to trigger each process, you could use a tag name, the same as an event extra. And doing that would allow you to have a single generic event trigger that only specifies exactly which process to launch based on the content of that tag in the notify that triggered the event. So in the ECL IDE, I've loaded both notify jobs, the first example, it's already up and running, and the job launch, which also introduces the event extra function that's reading the information from the XML tag. Right, let's go back over to our ECL Watch main page and let's go to the event scheduler. You see we have some other events now that are here. Job notify and job launch that are now lined up in the event scheduler. We can then jump over to our ECL code. You'll see then the hashtag work unit identified the name. We've got job notify here that is giving us results, even event, when the even event was triggered, and then also we go back over to our other output, which was result number 2, which is our odd event. And then this is the event that's happening every time, every 1 minute. We're notifying even and odd events that are occurring. So it looks like our event system is in place and working here in this particular work unit. Going back over to the second one that's allowing event extra, you can examine the outputs here. We have additional information in here. We push the event. Once again, we go back over to our outputs, and there's the even event that was triggered at the specific time, followed by the odd event that was launched at the specific time. And then as each cron job, each minute, we're then documenting that with notify run extra. This is the extra event that we talked about, and you see the dates and the times changing on the right hand side. All right, how's everybody doing out there? So this is our first 2 topics are now behind us, the cron jobs and the user-defined events. And we're about 27 minutes into our workshop. For the remaining 90 minutes or so, maybe less, we're going to go ahead and look at a real-world example. Code that was actually put into production, was working for quite a while, and probably, I would guess it's still in use. So when this was first conceived and written several years ago, we wrote it, we had it working, and then when Richard wanted to memorialize this and put it into a article book format, he decided to upgrade some of his standards to kind of refactor, clean up the code. So we're going to be looking at a lot of things. We're going to be looking at a lot of things that went into the design behind this. Remember, the end result of this real-world example is to automatically detect that files are waiting on the landing zone, spray them automatically into our cluster, add them automatically to a super file, and then do some data pre-processing, some data cleansing in the preparation of the data. Ready? Everybody, buckle up. Let's get into this starting right now. All right, let's talk about the plan, the design, and eventually the implementation. So in our first 2 sections of this workshop, we looked at key pieces to process automation. And now we'll expand on it with some real-world examples. We're going to create a tool to automatically spray files to your cluster whenever they appear on your environment's landing zone. And the tool we're going to demonstrate in this workshop will be JSON, and then actually starting with XML, then JSON. And you can take that code that will be in the repository and adjust it and change it for delimited files, CSV, or even flat files if need be. And once they're sprayed, the files will then be automatically processed by detecting the event in a standard manner, so they're then ready to work with. So what's the design behind this? data files come in periodically, sometimes daily, sometimes weekly, and so on. They need to be automatically processed in a standard manner whenever they show up, even without human intervention. So they'll often come in predefined formats and often as a batch. So this code is based on code that was put into production use over 8 years ago at the time of this recording. And here's the design overview. We're going to create a predefined semaphore file that arrives in the landing zone containing a list of files to automatically spray and process. These files must have already been transmitted to that same landing zone before the semaphore file arrives. So the actual files come first, then the semaphore file comes in and says, okay, let's go, we're ready to process these files. A DFU work unit monitors for the arrival of that semaphore file, checking by file name for its appearance every 15 minutes. And when the file appears, it pushes an event to launch the spray process. An ECL automatic spray process work unit is notified of the event pushed by the DFU work unit and then reads the semaphore file, spraying each file listed in turn. After each file is sprayed, additional events are then automatically pushed to further process the just sprayed file or files. And once all files have been sprayed, the semaphore file is automatically deleted from the landing zone so that another same name file can eventually replace it, nominating a new set of files to spray. All right, so that's the idea behind the design. And we're going to have so much stuff interspersed with that design. We also have some code that's going to generate some sample data for us, and we'll talk about the logic behind that. And we'll talk about the consolidation of these files into superfiles. And then with a single superfile read, we can then process and clean the files coming in, deduping them, cleaning them, uppercasing them, whatever we need to do. So let's start with, first of all of the factors that we need to know in order to properly complete this process. And so the first file we're actually going to step into and examine in good detail is an interface file. So an interface file is a very popular best practice used in ECL to help consolidate processes that have multiple parameters, and these parameters can change from time to time. For example, different file types for different events that need to be fired, different clusters. So moving your code from one cluster to another, you might have to change the reference to the landing zone and might have to change the IP address to the base cluster, all of these things. So we're going to examine this in more detail in an interface file. Notice the best practice that we immediately mention here is the name, starting with a lowercase I and then a root file here called auto spray files. Let's take a close look at this in more detail. But before we do, let's go back and check on our BWR code, our builder window runnable code that launched several. We had some cron jobs, we had a user-defined event, and let's go back and look at it. Let's go back over to our event scheduler. You'll see they're still in that wait state waiting for events. And I'm going to go ahead and terminate them right now because we're going to go ahead and start with a whole new process. We'll start with the real-world example of auto spray of files. So let's shut down and then see what happens here. I'm going to go ahead and select all of these events that are waiting, and I'm going to say, please, let's deschedule them. It asked me to confirm. I say okay. So these are now descheduled, which simply means that if I do a refresh of this browser, you'll see that they should now all be gone out of my event scheduler list. Also then, coming back into the ECL IDE, you'll see here that now all of the work units that I had, the job launch, here's the notify job, and I'm just focusing on the bottom now. I know part of this is cut off on the top, but we've already seen this. And also the original cron jobs has all been now released from that wait state. And I can go now into the IDE and examine all of the events that have been running, and you'll see here that there was an hour event that was posted here, so we have hourly runs that were posted. Of course, there wasn't any, when I recorded this, it wasn't at 12 noon, so we never got an event for that one. So you can go back and check. After you deschedule, you can go back to your IDEs, check the results, verify the events, and go from there. All right, let's dive into the interface. We start with the landing zone specifications, LZ. And there's two definitions here inside of the interface structure. The IP definition specifies the IP address of your environment's ESP server, which is also the host server for the environment's ECL watch. This is typically where the landing zone is hosted. The default is an empty string, so you'll always need to override this definition in your concrete instance of the interface that you use for production code. Now, barring that, you can instead just edit this definition to your environment's IP if you only have one cluster that you're going to be working with. And the LZ path definition specifies the path to the IP server to the actual landing zone. This default is also an empty string, so you will always need to override it or edit it to the default of your environment's landing zone path if you have one. Here's a tip. I'm going to jump over to the ECL watch of my current demo cluster. Okay, and if we go into the landing zone, note at the very top of the landing zone list is the actual path information that you need to specify in the LZ path. So this is very, very helpful. Go to your, if you don't know what your path to your landing zone is, you can either check out your environment variables, or you can just go to the landing zone itself, and always in parentheses, or not parentheses, but in brackets after the name of your landing zone, you always have the actual physical path to the actual landing zone location. All right, let's move on through the rest of the interface specs. Here we have the semaphore file specifications, starting with, of course, the flag file. The flag file definition actually names your semaphore file, and you'll always need to override this in your concrete instance of your interface. The next one is the flag file path definition, concatenating the semaphore file name to the LZ path in the previous slide. You'll always need to override this one in your concrete instance. And finally, the file to read definition translates the / directory delimiters to the double colons that the DFU uses so it can find the file. This default expression should only be overwritten if you absolutely need to, since it already covers what is needed in most concrete instances. Now let's look at the specifications for file import, or what we used to call the spray. We have two definitions here to talk about. The spray target definition, DIR, names the directory to spray onto the cluster. You'll always need to override this again in your concrete instance. This is analogous to the target scope setting you provide when you manually spray files using the ECL watch. And then also we have the target cluster definition, which names the target for the spray. So we have an if condition here because on a Kubernetes cluster, the default value uses the word data as the root folder of your target cluster. You should only override this in your concrete instance if your data plane name in your Kubernetes environment is not data. If you have a bare metal environment, the std.system.thorlib.group function should provide the correct name. Now let's look at some of the events that we're going to use to drive the auto spray, auto processing, and a little more. So the first one, the new file event, names the event that instigates the spray when the semaphore file has appeared on the landing zone. You should always override this in your concrete instance. The event to push definition becomes the event that instigates the processing of each individual file once it has been sprayed. You only need to override this in your concrete instance if you're automatically processing each file as they are sprayed. And finally, the event to launch definition names the event that instigates the processing of all the files after they have been sprayed and processed. You only need to override this in your concrete instance if you are automatically processing all files after they have been sprayed. This is a cool flag. It's called the file type flag. Again, in the interface, it's called spray type, and it identifies the file types of all the files listed in the semaphore file. You must always override this in your concrete instance. The value of 1 is a delimited spray, 2 is fixed, 3 is XML, and as shown here, 4 is JSON. Our CSV spray options, of course, some of these options you'll be familiar with: the field delimiter, the record delimiter, quote delimiter, and the escape character. These are all parameters that we use in our normal spray operations. So here's where you can set the default parameters. If you know that your record delimiter might change or your field delimiter is different from a comma, you will change it accordingly. Notice the double backslash there for the escape character that's being used in the ECL code. Here's our spray options for all files. The overwrite option to overwrite the file if it already exists on the cluster. The overwrite OK definition. We have replicate, which specifies whether to spray each part and also replicate each part. We know these. These are all the settings if you've sprayed any files using the ECL Watch or the DFU Plus for that matter. You'll know what these settings mean. We have also the compressed data, true or false, and pause seconds. Now this is an interesting one. This is one that you would not see. Pause secs definition specifies how long to pause between spraying each file listed in the semaphore file to allow the processing work unit to finish. This can prevent fast sprays from overloading slower processing jobs, and you should only override this in your concrete instance if you've tested your process and know that your automatic process job consistently takes longer than your spray, which could cause problems if the subsequent sprays are not delayed, thus allowing time for the previous file's processing to complete. So that covers our look at the base interface. Let's look at some other files in support of our process automation, starting with mod_events. Since we're going to be working with an auto spray automation, being an event-driven process, we're going to need to define some events, of course. So we'd create a module called mod_events and declare it as virtual because it will only be used as the template for each concrete module instance that inherits it. It only defines the most common requirements that all automated spray processes will require. And so we divided that into 4 separate events. Let's take a close look at these. First of all, at the top, we have the who definition. This should always be overwritten in your concrete events module that inherits this one. And doing that allows you to make the actual events for each real-world implementation unique to that one set of processes. That way you can always have as many implementations of AutoSpray active and operating in your environment as you need, all at the same time. The spray, process, launch, and final definitions all concatenate the who definition's unique value to standard constants and make it easy to see which work units are monitoring for which specific events. This will all become clear when we create several implementations of all of this later on in our workshop. All right, another module that we have in our code repository is called mod_utils, for utilities, of course. We have 3 functions here that we're going to talk about briefly. First one is called raw file name. It parses a standard path and file name from the DFU, which uses double colons as the directory delimiter to extract just the file name portion. Next we have cap_, which parses a full path and returns a string with a caret character prepended to each uppercase letter. This was a requirement, of course, when working with the distributed file utility in Linux. And then finally we have the pause function, which is an ECL wrapper around a C++ sleep function. So the first one, raw file name, here is the function embedded inside of the module. You see it's taking advantage of the use split words and then a count and then returning the reference to the particular split based on the number of words in the count function. So it starts by using the split word standard library function to parse the passed-in file name argument into the individual elements in the splits set. And then it uses the double colon directory delimiter as the indicator for how to split each element into a separate word in the set. The split count definition then uses the count function to determine the number of elements in the set, and that allows the function to return the last element in the split set, which would be the file name. So that's how that works. So we're just going into the long string with the directory and path, parsing through the double colons, and then the very last element will be the name of the file that we need to deal with. Cap character is an interesting function. It just defines a set of uppercase letters. It looks for those uppercase letters and then appends the caret character to them. So in this workshop, we only needed the support for the English language. So if you're working with other languages, you may need to alter the contents of this set. The CARS definition inside of cap caret provides the number of characters in the pass file name argument. And then finally, the data set here uses the CARS characters, CHARS value to separate the separate record for each original letter, and then prepended each uppercase letter with the caret character. All right, so just a lot of internal processing going on to move and prepend a character in front of the uppercase. I'm having trouble with that today. I don't know why. Let's move on. There's the roll-up that makes that all happen, appending the left character plus the right character. And then finally the return expression returns the single string. So if your pass file name contains the following there, then the return string after cap caret will be all of the uppercase characters prepended with the character, which will allow the Linux file system to actually find the file. That's required by Linux, and that's why we had to do that. Now the last one in the utilities is called pause. This is the one that's fairly simple to implement and use, but once again we want to explain why this is needed. When you have a job in a separate work unit and it must complete before it can go back to waiting for the next instance of the event, it can cause it to miss launch events if our window is too small. So in that case, you can kind of tweak the performance of it to actually slow down the performance of HPCC and ECL by using the pause function to delay the start of the next spray by the number of seconds you specify, thereby giving you the process job time to complete. How long the delay will have to be determined by your own experimentation, but we'll be using one in this example in the workshop to show you how this was implemented. All right, time to take this real-world example down the home stretch, but we still have a long way to go. We're still going to talk about building some... We actually have like a side path that we're going to take with this where we're going to build some sample data. Now, a lot of times you're going to have the data coming in and you're not going to need to do this. But just for testing purposes, we needed to do this. We had a module that's going to generate some sample XML sales data, some sample JSON sales data, and then we'll go ahead and test the spray operation using those sample files. Let's go. Here we go. So all of the logic that we need to auto spray files is encapsulated in a single module. That single module also then pulls in all of the necessary parameters from the interface that we just talked about a few moments ago. So here is the start of mod_auto spray files. Pretty simple start, basic stuff. We begin with a standard import for the current directory, which is the $sign reference. And then the ECL standard library, which is importing the base STD folder. Now, normally we don't like to do this in ECL training, but because of the amount of parameters from the interface, we wanted to simplify our code. So we have a single parameter named P that will be referenced many times in this module. So in this case, we just chose brevity over verbosity. All right, moving inside the module, you'll see we have a record defined with a file name, a size, and then a tag, variable length string. The landing zone file name is prepended with a tilde, the word file, colon, colon, always a constant. Then the caret around the file name to put the carets if anything is uppercased, and then concatenate another double colon and concatenate the actual file name to read. The landing zone DS dataset definition declares the semaphore file for use in the rest of our ECL code. The file count definition determines the number of records in the semaphore file, and the max files definition is a constant that specifies the maximum number of files that can be sprayed as a single batch. And we'll cover this a little bit later, why we needed to do this. Some more prep work. We have the full file function that creates the full DFU path and file name for each sprayed file. We have a spray message action that writes a log entry to the spray progress result for the work unit that sprays the file. And the delete semaphore definition removes the semaphore file from the landing zone after all files have been sprayed. So it looks for an event once all the files have been sprayed and says spray complete. Then we delete that semaphore file that sets up the wait for another appearance of that file to initiate spraying another batch of files. A little more prep work here. We have a timestamp, standard stuff, today's date and the current time. And then we have our event message, which is logging the events to be pushed. This adds a pass string argument to the work unit's info queue, which displays at the bottom of the work unit's summary page in ECL Watch. So once again, inside module auto spray files, everything is happening here. And now we have an exported wait for file definition. And this is the exported definition that you will use in production code to initiate the entire automatic file spray process. It uses std.file.monitorFile, the standard library action, which launches a DFU work unit that checks the landing zone periodically for your semaphore file. Once the file appears, it pushes that new file event to the environment, which the work unit waiting for that event will now notice and start its work. The default monitor period in the DFU is 15 minutes, 900 seconds. This is our monitor interval setting. The setting can be found in your environment.xml file for bare metal configurations and in the values.yaml for Kubernetes configurations. So we also have a function now that will take two parameters. The file is the file to spray, and the record size is the maximum length of any record. This is the function that sprays any type of delimited file. Now, inside it uses the std.file.spray delimiter shown at the top from the ECL standard library to execute the spray operation, passing it parameters from the P concrete instance of the autospray files interface passed to the mod_autospray files module. This is one we're not going to do in this workshop. It's here though so you can implement it if needed, but we're going to be demonstrating the actual XML spray function and then the JSON spray function shown on, well, here's fix. And this is another one we won't be using, but it's available if you need to use it. So there's fix, there is the delimited in the previous slide, then we have our XML spray function. Once again, we pretty much just copied the reference to the function, the std.file.sprayXML, and then all of the necessary parameters that it needs. These are ECL libraries that have been around for a long time that allow us to automate the spray process. And so now in this workshop, we're actually going to put them into action. So we have the XML spray, and then finally we have the JSON spray. All of these inside of mod_auto spray files. All right, so let's take all of these parameters and functions that we've created, and let's put them all together now and tie them to an event-driven process. Let's complete this module in the next few slides. Here's some information on the import and process actions. We have two functions here. One is called file EX and the other one is called event EX. Now, the only way to pass information about a specific instance of any event handling process is through an XML string. And that XML string must be in the following format. We kind of reviewed this earlier in this workshop talking about the event extra function, which requires the actual information in the string to be contained within the required event tags, nested within other tags that you create, represented, for example, here as my tag. All right, and then, so these two functions here, event X and file X, work together to create the XML string for each sprayed file to pass the name of the current file to act upon to the process code. The result will look like this. You'll have the event and the file name, name of the file inside of the tag, close event, close file name tag. All right, our actions to process each file, we have another function called push event. Push event actually is passing a parameter to a action called ordered. Once again, ordered is a form of sequential, and we talked about that earlier, the use of ordered. The push event function does exactly two things in sequence, using the ordered action to specify the execution order. First thing it does, as you see in the list up above, is it uses the notify function, triggers the event to system-wide to any work unit waiting for that event, and then passing also the name of the current file to process from the file argument of event X in the notify function's second parameter. Then we talked about earlier this function called event message. Previous slides, you can go back and look at that. It posts information using the standard function library to the work unit, noting the time in the event that was triggered for the particular file in question. So next is the action to trigger the post-spray final event. So after all the sprays are done, so you're going to see we have some very elegant code here that will walk through the spray process. At the very end of it, though, we have to let the system know that the process is now complete, and they can go ahead and delete the semaphore file and start all over again waiting for a new event. So this is called the push final event function. And so it does actually three things in sequence, once again using the ordered action to specify the execution order. First of all, we have an output action which writes a copy of the semaphore file to the spray target directory, overriding any previous version that may have been there. This saves it for use by the work unit that's waiting for the event to launch to commence its work. Next, we have the notify function, which triggers the event that your final work unit is waiting for, passing the name of the semaphore file from the file argument to process in the notify function's second parameter. And third, we have the event message function, once again wrapped in ordered, that posts the information message to the actual work unit, noting the time and event that was triggered for the file. Here we have then also in this module the action to actually spray or import a file in the semaphore file. So this is actually what's happening here. So let's talk about this area marked in yellow first, then we'll jump into the if condition. Message 1 and message 2 are defined separately from where they're used just for better code organization. We've got one message that says spraying the file, and then we also have another kind of an error message that says no spray type specified. So The spray one function accomplishes the actual spray operation. So there it is on the third line there, marked in yellow, passing it a number, which is the type of file that needs to be sprayed. And the spray function accomplishes the actual spray operation using the if function that we're going to examine a little bit further in the next slide to detect whether there is a numeric entry in the semaphore file that contains the name of the file to spray. If not, it simply does nothing. A false expression is not required when a true expression is an action. So now, yes, we have here inside the if, we have the ordered again, which will execute these three things in sequence, starting with the spray message function that adds the message one text for the current file to the spray progress log file for the work unit. What file are we going to spray? What's the file name? Then we jump into the case and if. The case function calls the appropriate spray function based on the spray type value from the interface, or defaults using the spray message function, adding the message to text that says no spray type specified, and then again dropping out of the process. Number 3, the if function at the bottom here detects whether there is a valid spray type value and a non-blank type event to push. If both are true, it then uses the ordered action nested in that if to call push event to launch the process work unit, followed by a pause function that pauses for a number of seconds in between spray operations. And now I want to introduce you to something a little bit outside of ECL, but something that's been around since the start of ECL. It's the template language. This template language right here simply constructs an ECL language statement that is based on the number of files that you have specified. So you have a start of this set spray string which says ordered spray 1. There'll always be at least the first file there. And then based on the index, it will generate as many spray 1 with a numeric value after it to generate the appropriate string that will be sent to the spray 1 function in the previous slide. So once again, you've got a spray all files definition at the very bottom that is going to generate and construct this spray string. And the spray string will then be sent to the spray string, as you see below here, has this ordered statement, and this is what actually will get generated by the template language. Kind of a clever way of doing this. So based on the number of files that you set in the max files constant, it will generate spray 1 through spray n based on the maximum number of files. Notice inside of the template language it uses that max files value to break the loop when the max files number is exceeded by the index. Pretty cool stuff. All right, so the ordered statement here, let's talk about that. It calls the spray 1 action to spray up to 4 files based on the maximum. We set maximum files to 4, passing each record number in the semaphore file to the spray 1 action. And if you want to allow a different maximum number of files, you just change the max files definition value in the interface. Okay, and finally, we get to the actual spraying the files inside of the, again, an ordered statement. This is called the spray them action. It uses the ordered action to specify the execution order. And after everything is sprayed, it will then, so after the spray all files is executed, then we have an if condition here that says if the event to launch is not equal to blank, then we're going to push the final event, put a spray message, and then call another definition that will actually delete the semaphore file and make room for a new one. So the spray them action uses the ordered action to specify the execution order. We spray all the files with the spray all files action. Number 2, we push the event to launch. And then number 3, the spray message function adds text to the spray progress log file for the work unit. And finally, number 4, the delete semaphore action deletes a semaphore file from the landing zone. That's it. So once again, this whole process, mod auto spray files, gets the files from the landing zone onto the cluster automatically based on events. All right, so the last part of this module, it makes a decision here to either spray or fail for too many files in the batch. So once again, if you've got too many files on the landing zone location, it will abort the auto spray process, and then human intervention here. Now again, you can modify this, or you could just say spray everything that's out there regardless. You can take that code and modify it if you want to, but just the system requirements that we had here for our people that were using this in our company, they decided they needed to have kind of a ceiling here of how many files they wanted to bring in. So once again, there's just a simple if condition here that says if the file count is less than or equal to maximum files, then go ahead and spray them. Otherwise, just we've exceeded the number, we post a message that says too many files, delete the semaphore file, and abort the process. All right, how's everybody doing out there? Thank you for hanging in there with me. We are over halfway through the workshop, and we're going to take it home now with some really good stuff. This next section will actually take all of the preparation, utilities, interface, events, everything we just talked about in our first hour, and now we're going to implement it in a simple XML demo. When the requirements of this project was brought to us, we wanted to know exactly what these files were going to be looking like, and based on sales data. So we decided to really give this a good test, to write some other utilities that would generate the sample files that will actually emulate the real files that we're going to be working with in practice. So we're going to take a look at we're going to go off the path now. We've talked about the event handling and process automation. We're going to put it all into action now in this next section, but we're going to go off on a couple of side roads here and talk about some really core good ECL stuff. How to generate sample records, how to generate parent-child relationships, nested child data sets, how to generate an XML file, how to output a file with ECL directly to your landing zone. This is a great set of tools that you're going to be looking at here, and it's constructed in a way that you can extract what you need in your own projects. So without further ado, let's strap in, get comfortable again, refresh your beverage, and let's talk about implementing our auto spray tool with the XML demo. All right, so before we start on an examination of the code slide by slide, let's just actually run this code, and then we'll come back to it and actually see the auto spray and processing in action. So looking over to the left side here, I've got my repo set up in a working folder. I've called mine process automation, but it's the exact same code that you'll see in the code repository that's on our GitHub for this workshop. Now, just to zoom in, you'll see that you have a subfolder here called XML demo, another one called JSON demo, and you can modify this code and add your own CSV demo and your fixed length demo if you choose to do so. Once again, the core code for auto spraying our files is located in this module in the root folder called mod_auto spray files. And all the code that I just talked about in the previous slides is all now listed here. The key linchpin to get this all started is to monitor and wait for the semaphore file that we talked about on the landing zone. Once this is detected, then you'll see, well, to launch this, we have a simple BWR file here that waits for the file. So once again, going back over to that module, there is the wait for file, waiting for the existence of the semaphore file. Once the semaphore file gets detected, it then will generate the event that'll call the spray files definition, which goes through and starts to process all the files from the landing zone onto the cluster. After that, sprayed into the cluster, a process event's generated that will then go into this section of code here, which is simply adding it to a super file. Now, this is just the tip of the iceberg. As I mentioned, this is bringing the data in, adding it to a super file, but of course, you could then go from there and start to do your dedupes and roll-ups or anything else that you want to do, the cleansing of the file if necessary, and so on. So, the launch of everything, I've launched the Spray XML, and you can see that it is in a wait state in the scheduler on my cluster, as well as the process XML. They're waiting for events. Now, going over to the ECL Watch, yeah, here is the work unit that is waiting for the events, Spray XML. I could go over to the landing zone right now, and I will show you in our landing zone in our training cluster, we have a folder called Process Auto. And notice the Process Auto folder is right now empty. So these BWR files have been running all night on the cluster waiting for an event. Please give me events. Give me an event so I can run my code. All right? So we're going to do that right now. Getting back over to our ECL IDE, I'm actually going to go ahead and generate the sales files. And we're going to be reviewing this code in the next couple of slides. But it all works with, first of all, outputting the semaphore file and then also outputting the various XML files that we're going to be building from scratch. I've even added some debug code in this gen sales file, so be careful. The thing that actually gets us to work is actually the last line, which is the sequential operation. First of all, generate the individual XML files that are going to be appearing on the landing zone, then finally generate the semaphore file. As soon as I execute those, these will be executed sequentially, and then we will go back and check our landing zone to look for the existence of those files. As I mentioned, I also have some debugging code here. If you want to check, make sure your LZ path is correct and your file name is actually correct as well. The file path name is being generated correctly. These are just some debugging tools. And also I had a little debugging here that was just generating the semaphore file, which I'm going to comment that out as well, because that's going to be generated by my sequential. All right, so in addition, you see I've got my LZ path at the top here. Really, I'm kind of breaking one of my rules. I'm putting the LZ path here, and there's also a interface here where there's an LZ path, so be careful with that. I could have just referenced the LZ path that was in the interface, but I decided, just so I could see what I was doing, I decided just to make a copy of it for testing. So, and the other thing I noticed too is that if you designate a folder that doesn't exist, it will create the folder for you automatically. So here we go. Just modifying one last check here. It looks like our outputs look good. I'm going to go ahead and do a syntax check. And let's go ahead and submit this. It will connect to the cluster. Very quickly should generate, you should get a feedback right away. If you get a delay here, it's meaning it might have problems connecting to your cluster. So that's a telltale sign. So no, my code executed very quickly. It's done. And now I can go out to my ECL Watch, and I can then hit the refresh on this landing zone, go into my Process Auto, and you'll see now that we have not only our semaphore file here, xmlspray.csv, but also the 3 XML files that are going to be sprayed. So we'll get back to this code in a little while and watch what happened. So let's dive in now to the examination of the actual code itself. And so the first bit of code we're going to look at is an ECL file called gen_sales_rec. This is in the root of your code repository. This code demonstrates techniques for generating test data and emulating working with the files that contain additional data to add on a periodic basis. It's going to generate daily sales data for a 100 store chain of dollar stores where items are sold for $1 to $5. The result is a nested child data set where each store record for a given date contains a child data set containing a sales record for each SKU, showing how many were sold and the total revenue for that SKU on that day. Since both XML and JSON examples will use the same type of data, we created a single record generator to use for both. The actual data will be different in each. So let's start with the first thing you always do. You always get your data defined properly. Since our data is going to be generated on the cluster, we didn't need to import anything. We're going to be generating this data from scratch. So first thing just to look at on the right side here, we have the capit function, which is just a more elegant way of referencing our cap-caret function to simplify the code. Then we've got a couple of records here. The SKU record is the actual child record, as I mentioned in the previous slide, and for lack of a better name, we have rec, which is our parent record, which contains a store ID and the transaction date, and then of course for each transaction date the child record will give you the SKU, the number sold, and the total amount of revenue. All right, a few definitions here of note. We have the gen SKU definition that uses the letters definition above and IDX to generate a random 5-character SKU to use as a product identifier, starting with an uppercase letter followed by a 4-digit number. Also, we have a SKU count, which defines the number of products sold in each store. The record count, RECCNT, uses stores and days to define the total number of parent records to generate. So in this case, stores times days, we have 100 stores times 3 gives us a 300 parent records. Says our intention here is to create these days of sales for a 100 store chain. 3 days of sales for a 100 store chain. All right, the SKUs function takes no parameters because it always generates the number of SKU records defined by the SKU count. That's a new form of data set if you haven't seen it before. This can generate data sets on the fly. So the number of SKUs plus 100, and then the transform that will generate the random SKU numbers accordingly, random price, and of course a dedupe that's also in place here to remove any duplicate SKU value records. And then the square brackets eliminate the extra records, so the function only returns the correct number of records that we're generating. Now, interestingly enough, here's the first. Some of you may or may not have ever seen this before, but here's a workflow service called Independent. Independent appended to this function definition ensures that the record set of SKUs is generated globally and only once for the work unit, so that all code for the rest of the work unit uses the same set of data records. And then we take advantage of another new technique in ECL. This has been around for a few years, but it's one of the newer statements. It's called dictionary. It's a in-memory lookup table. And so we build from our SKUs an index into the SKUs by the SKU value and return the price. And then the SKU price function uses that SKU underscore DCT to return the price for a particular SKU. Moving on in our Gen Sales Record ECL, the sales definition shown at the top here generates the total number of sales records for all of the generated data as defined by our record count times the SKU count. It does this with a dataset statement that generates records with a unique ID field generated by the actual counter and random C field values between 1 and your SKU count that will represent the number of, quote, sales in one day for a particular SKU. And once again, we bring the dictionary into the picture, another dictionary called Sales DCT, which provides an index into the sales by the ID value to return the C value. Then the sales count function uses that sales DCT to return the C value for a particular ID. This function is used to populate the actual sales numbers for each SKU each day. And we also have a dates function here, which remember we were going to be generating different days of sales. So the dates function creates a set of these dates for which to generate sales records. And by producing a set at the end of this, the function returns a set. Subsequent code can use the date values by simply indexing into that set. The GD Gregorian date definition uses the today function from the date standard library to get the date into an unsigned for in year, month, day format. And then the Julian date uses the from Gregorian date function to get the number of days since January 1st, 1 AD for that Gregorian date. All right, completing the dates function, the C2JD function takes an integer parameter and uses the to Gregorian date function to return, once again, the year, month, day values for the days preceding the Gregorian date, GD. And then the dataset definition creates a dataset of the year, month, day values for all the days preceding the Gregorian date. Return expression creates a set of unsigned fors to return by using the set function on the sorted data set to create a set of its D values and then appending it to the Gregorian date one element set. All right, generating store records for each date then. We have a genrex definition, once again calling the data set, using the record count as the number of records to generate. And we generate records based on the record count definition, our case 300, creating parent records of the nested child data set that will contain all of the generated data. All right, we populate each record store ID with the store identifier number, in this case a number from 1 to 100. The transdate field contains the ordinal position of which date to use from the date set, in this case the numbers 1 through 3. And the sales field is initialized to an empty set to be populated later. That's our nested child data set. The results in the set of parent records for the nested child data set where the store ID and the transdate fields constitute a unique key, and each store ID number appears in 3 records, each with a different transaction date, transdate. Here's a function called generate SKUs, which generates the sales nested child dataset records for one store ID, passed as the ID parameter on one particular date, passed as the DT parameter, uses the project operation on the previously defined SKUs record set to create the record set. And then the start function inside the transform, embedded within the transform, uses the ID and DT parameters as well to calculate the starting point within the sales data set for the previously generated sales numbers for each specific store ID and date value. All right, so we generate a sales record for each SKU. And again, I generated this data, and it was very quick, as you saw in before we started the slide presentation, to generate these data, this data set, chop it into 3 separate files, and then spray it onto our landing zone. We'll check on that in just a little while. So to wrap this up, we also have inside the transform, that transform that was on the previous slide here, the start function was just at the top of the transform, and then the rest of the transform is shown on this slide. I had to split it up because of just the size of it. The self.sku field gets the left SKU field value from the SKU data set, which was our parent, while the total amount field defaults to 0. And then the C definition value comes from the sales count dictionary function, passing it the ID record number to get by adding the counter value to the return value from the start function. This is then used in the number sold expression and the total amount field. All right, so finally, we have another thing called sold report. So again, this is how much was sold on each day. And there's a clever function that's in the root called position in set, which gets the ordinal position of the transaction date in the date set to pass on to the gen_sku function. All right, so this transform here processes our generated records, adds to our generated records. And the whole thing then wraps around a gen sales rex module, 2 returns here. allows us to use both the generated data, which is the recs, and the set of dates for the data. That way we can use the data generated to populate the data that we will write for the workshop's 2 examples. The first will work with XML files, while the second will be with JSON files. All right, before we continue, let's step out again to the ECL Watch and take a look at our landing zone. And notice that the semaphore file has vanished. The XML files are still in the landing zone, but the semaphore file has vanished. So we can take a look at the DFU work units, and you will see here that the file was being monitored. The semaphore file was detected. It launched the spray operations. It sprayed both the for the last 3 days, sales for the last 3 days. Now this was recorded on August the 24th, so we have August the 22nd, August the 23rd, and August the 24th. Finally verifying in the logical files of our ECL Watch that indeed we have not only 3 files that were sprayed, but also added to a super file. So we could, if we wanted to, open up that super file. We could look at the contents of it, and you'll see all of the XML data there accordingly, nice and ready to be processed, ready to be transformed. So it looks like it works. So now let's go into how the XML file was generated, and then let's wrap up this process and then take a quick peek at JSON. All right, so the gen sales file module we just looked at was generating the data in memory, and of course we want to be able to test this for all file types. So we've got a little module here that will generate the XML, and then we'll apply that also to our JSON example as we get close to wrapping up our workshop. So again, now that we have the code to generate data records, we're going to use it to create some XML files. And then we'll also review the settings along with the semaphore file and the auto spray override of our interface. And of course, we process then by an event, we process the XML files that were sitting on the landing zone. We made a super file of them, and we are now ready to continue from that point. All right, so let's start first of all, of course, by defining the layout of the files. We have a file called sales.ecl. This is the name of our super file here, marked in yellow at the top, and then, of course, at the bottom, the dataset definition. Here's our, once again, parent-child relationships, pretty much just defining what we had in memory and then applying it with XPath statements required. Now, it isn't really required, but it's just kind of a best practice here by the author. But ECL has the ability to recognize tag information just by the matching tag, as long as it's not ambiguous, meaning that, for example, in SKU, there's not a lowercase SKU and an uppercase SKU. All right, so of course the SF name definition is the name of the super file that will contain all the files that were sprayed. Once again, we use XPath to explicitly define the tag. And probably, like I said, we could have gotten away with it if our tags matched the field names. But this allows us to override the field names if we ever need to do that. And of course, the XML dataset row is the standard HPCC definition when we generate the output statement. So we have a mod underscore events ECL in the XML folder. We're telling that all of the events that's going to be happening here will be of the XML file type. That's what that who means. So later on, if I wanted to do JSON, I'll have who defined as JSON and so on. Here's the interface that overrides all of the information that you need, the pointing to the appropriate landing zone path, the name of our semaphore file, which we're calling in the XML example, xmlspray.csv. My target prefix of the file is workshop : in : concatenating that with the name of the file. There's what we intend to do in this is to spray and then process, which I just showed you. Spray type 3, which is equivalent to XML, and then we're going to pause 5 seconds between each spray operation. Now, I do want to say something there that when I was testing this, and just to make sure that the spray code was working independent of events, forcing the spray to happen when I wanted it to, I wrote some code to say, go spray those files, and then having the pause on it, it was kind of interesting to watch then, because you could actually see the work unit, first of all, go into a green mode that would say, yes, I'm spraying right now, and then stop for 5 seconds, and then spray the next file and stop for 5 seconds, and so on. So it's really a cool thing to watch. It works just as advertised. All right, so there's our settings that we use in the local folder of XML to override things like our landing zone path and the name of our semaphore file. All right, a couple more notes on the interface. If you're working in a shop where you only have a single HPCC cluster, then you could simply make that environment's IP and LZ paths the defaults, which would eliminate the need to do the override like we're showing you here. If you have more than one, though, leaving the defaults empty would be the best way to go. And of course, you could also default to the most common environment, which would only require overriding for special projects to other environments. Also, you notice if you take a look at that interface, we also use the containerized compile time constant, because while we were developing this workshop, we also tested on both Docker and VirtualBox bare metal to ensure it works with both. The if function automatically detects whether the platform is running on Docker or VirtualBox, making the IP setting appropriate for each. And the flag file and spray target definitions always need to be overridden because they're always going to be specific to your project. And the new file event and event to push definitions are overridden here because they are defaulted to blank in the root interface. And this could also be defaulted to the standard mod events entries in the root interface and only overridden when applicable. Lots of flexibility here. Your spray type definition always needs to be overridden because it's always going to be specific to the project. And of course, then finally, your pause seconds definition is overridden here because I wanted to allow a 5-second pause to make sure your process code has time to execute and reset itself to process the next file. Fair enough? Here's our process code. Not much to see here if you've seen ECL before. We're looking for the existence of a super file. If it exists, we leave it alone. Otherwise, we create the file. Then we're just adding the super file. So as each file is getting sprayed, then we call this process, which adds it in turn to our super file. And so, yeah, you could do this, and then after this is finished, you could spawn another event that would then continue it through its transformation process. And then you would sleep well with ECL, wake up in the morning, and all of your data has been processed and ready to roll. All right, we again here look at the extra event, which extracts the file name tag from the XML as the notify function's second parameter. Then notify is coming from the push event function in mod_autospray files discussed previously, which instigates the execution of this work unit to process each file after it has been sprayed. All right, so then there's some information here about the super file name. Again, we detect if it exists, and that's the if that I just talked about. No reason to talk about it again. The add file definition, we talked about that using sequential, and then the log text gives us a log entry to tell us what's been happening, and there we go. All right, so the last file we're looking at here, BWR Gen Sales Files, was the first one I ran when we started this block of information, the XML demo. And so we had the spray file and process file already in the scheduling queue waiting for events. We generated the sales files, which actually generated it to our landing zone and created the semaphore file at the same time using the ordered sequential actions. And so those files then existed on the landing file. This simulates the FTPing of data files to your landing zone, of course. That's all they're saying here. So instead of me going out manually opening up FileZilla or some FTP program and then manually uploading files to my landing zone. We just generated it from the ECL cluster. And along the way, you have a lot of good code that you can take home with you and use it in whatever other projects you need. It doesn't have to be an event-driven project. You can use the code just to generate sample data when the need arises. All right, so the capit function, once again, was used purely for cosmetic purposes. We call it several times where it would have caused code formatting problems in the presentation. The sold report definition we looked at previously, that was using the project to build the actual data in memory. And the dates definition retrieves a set of dates used for the data generation that's going to be included in the file names and the data itself. So here is our concatenation of our landing zone. To read and write, we just simply begin with the tilde file : that's the magic behind it, followed by the IP of your landing zone, and then any folder that you want to throw it into. I put it into a folder because my training landing zone had several hundred files that I never would have been able to show you the demo cleanly without its having a nice subfolder in the landing zone. All right, and then the LZ file name function builds the individual file names, as I just discussed, adding the date element into and then appending it to an XML extension. All right, and then here is the magic. So inside of this parallel operation FTP files, which we're not really FTPing, but we're saying if you were FTPing, this is how it would work. We're just outputting 3 files to the landing zone, splitting it into the individual 100 stores. So we have the first 100 records on the first day, the second 100, and then the third 100 on the third day. All right. And so these actions can also execute in parallel. There's no reason why they shouldn't. No reason to use sequential on this one. So it's only telling the compiler that parallel execution is okay to do if the compiler chooses to do so. All right. Each output action, like I mentioned, writes out 100 records. The first will be from the first date and so on. Okay. This is creating the semaphore file, just very simply, again, dropping in the names of the files, creating a data. So there's only going to be 3 files in this semaphore. If you wanted to have more files, you could add more files accordingly. Just to make sure that your file names and the file names that are being attached with the semaphore file match, all right, or the spray will fail. And that's pretty much it. A lot straightforward stuff here. This is emulating the action right here that we see here, FTP semaphore, actually will create the semaphore file. And so it writes the semaphore file to your landing zone, and then finally down here, putting it into a sequential operation, we also then write the data files, fully written before the semaphore file is created. So the semaphore file would not happen if something happened with FTP files and the files were not output properly. Then there would be no reason for a semaphore file to be created. And so in your code repo, to demonstrate the activity of auto spray and then auto process, you first run BWR process XML. That will put it into the event queue in your scheduler, and then run BWR spray. That will then put that into the queue. And then, of course, you'll then either FTP your files to your landing zone or use the gen sales files that are in the repo to generate some sample data so you can actually study and view the execution, the event-driven process automation that we have here. Okay, so to wrap this up, remember we started this XML demo by running this file called BWR_gen sales file. So the sequence of events is in your code repo, you'll have a BWR spray files, BWR process files. Run the process files first, then run spray files. It'll put it into the event scheduler. Then run your BWR_gen sales files. Now, of course, make sure that all of your interface settings are correct. That's critical. Make sure that you're pointing to your cluster correctly with the correct IP address. Make sure your landing zone matches the landing zone that's defined by your environment, and so on. Once you do that, it's a pretty straightforward process. You can just sleep well with ECL and watch it run. When it's all finished, there it is. You'll see in the logical files listing, you'll see your super file being created, the XML files being sprayed accordingly, and from there we can proceed to process and move on. All right, I hoped you liked that as much as I liked presenting it to you. That was some really good stuff there in the last section. And now in this section, we're going to just shift gears and change our XML file format to JSON. There's a lot of just simple things that we need to do to shift that focus, and we're going to do that right now. All right, so now that we've automatically sprayed XML files, we can do the same with JSON files with just a couple of modifications. And because this example is extremely similar to the previous XML example, we're only going to look at the differences between the two sets of code. Well, we'll start with the sales.ecl. Now again, this is the sales.ecl in the JSON demo folder. So we have an XML demo, we have a JSON demo. In sales.ecl in the JSON, we've made a couple of changes. Starting with, of course, the name of the superfile. So instead of XML files, it's superfile_JSON files. We also have made a change to the XPath of the nested child information, and then also the JSON file type with the appropriate row tag as shown in the dataset statement at the bottom. All right. So, and that's the standard JSON row tag that's generated by the output statement of ECL. In mod events, under the JSON folder, we simply change the who definition from XML to JSON. Nothing else here that we need to see. Here is the interface where we, of course, give a new semaphore name, jsonspray.csv. Then, of course, the spray type changes from a 3 to a 4. Everything else, once again, stays the same, except we did add a new event here called a final event to push once all files have been sprayed. We'll explain that in an upcoming slide here. So once again, we have a BWR process JSON where we had process XML. This is the one we'll run first. It'll put it into the event scheduler. No differences here. They both just add the newly sprayed files to the super file. And then we have our spray JSON, which once again works the same way. It waits for the semaphore file to exist on the cluster, and then we'll instigate the spray files process. And the only difference is the replacement of XML with JSON in each line. Finally, in gen sales files, once again, we emulate the FTPing by changing the FTP files definition to JSON files this time instead of XML. The semaphore file also is using JSON as the file type. So those are the only differences that we have in gen sales files. And so when you want to test your JSON code, making sure all your settings are pointing to the right cluster, then first generate the actual files that will be copied to your landing zone. That's number one. Second, you'll run BWR process JSON to put into the event scheduler, and then spray JSON. So remember, first in, last in, first out. So here we go. That's really about it. And then our final processing here, this code here in BWR gen stats JSON. This is something we added. This generates the same stats of the 4 output actions in gen stats XML. However, this produces a 1 record data set with 1 string field containing the 2 sales total values and the 2 nested child data sets, which is sales per store and sales per store by date. The when workflow service waits for the final event and then generates this information to you. And that, as we say, everybody, is a wrap. And that wraps it up, everyone. We made it. Thanks for hanging in there again, and I hope you enjoyed this ECL workshop. It was a labor of love putting together all of the content and presenting it to you. And please, 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 if you have any questions, download the repo, start to look at the code, and if you have any questions about any aspects of it, please contact either myself, there's my email right below the thank you, and also a big thanks to our moderator, Ugo Watanuki, who was also here and present during the workshop. So thank you to all. Enjoy the rest of the week. We've got a packed week full of great stuff, and I hope you enjoy it. Thanks. Enjoy the week. Enjoy the Community Summit. Bye-bye.